Hello and welcome to Networking Essentials 1.0 Chapter 1. This chapter is titled Ever Wonder How It Works? Today we're going to talk a little bit about how you can pull the curtain back in a very Wizard of Oz type of manner and see what's going on our networks and how those networks are supporting what we do each and every day. The first question, or the items we want to be able to do at the end of this chapter, are explain the concept of network communication, so how devices communicate on a network. Explain the roles of devices such as end devices, intermediary devices, client servers, those items. And then we will build a functioning network, a simple functioning network at the end. Are you online? It's kind of a rhetorical question because of course you are. You're online, you're watching this video. That's the type of change that has occurred recently that allow us to really be more connected than ever. Our phones are connected to the internet. Our cars through Android Auto and Apple CarPlay. Our tablets, our TVs, our gaming consoles, even items like our front doors that can now be unlocked and locked with a phone are connected via the internet. This has given us great opportunities and also great risk as we move forward. Really, who owns the internet? Well, no one does at this point. It's controlled by a group of standards organizations. It is used by us for many things. Again, this video you're watching here is very similar to a video conference. It allows you to connect with anyone around the globe. I have friends in Germany that I can Skype with, no problem. People I know all over the world I can Skype with at a moment's notice. So it's very interesting. We also can, get push feeds for our news. We can play online games via Xbox Live, PlayStation Network. We can connect our phones and text and send information. In fact, just this morning I was texting someone in Germany. So it's pretty amazing how connected we are via this thing called the internet. Now, all of this really starts with a local network. The internet is simply a connection or a collection of local area networks. Now, a LAN, or local area network, can also be what's called a small office, home office. So we can have a small home network, which is just one PC, or like in my house, several PCs, a couple consoles, gaming consoles, and a TV, or a couple TVs connected to the internet. That's a small home network. You can have a SOHO, small office, home office, which is a network that consists of, let's say it's a small business with 5 computers, a server, and an internet connection. It can be a medium to large network. This is where we're getting into what's called a LAN, a local area network. Now, a local area network is a network that is within a limited geographical area. That's how you can remember that. Local area network is a limited area network. All right, so it's within a small limited area. Normally we say within, a couple buildings in a single city, and by that we mean a couple buildings clustered within a city. We do have some other concepts or different names for networks called a CAN, a campus area network. That'd be a college campus or a company with a campus has multiple buildings in the same area. We have what's called a metropolitan area network, a MAN. A metropolitan area network is a group of different buildings within a city that are connected. And then we have the wide area network, so the WANs. The WAN is simply a group of LANs connected together. So the internet is just a big WAN consisting of all the other networks in the world connected together. How do we make those connections? Well, we've got all types of devices. We've got our phones. We've got our tablets. We've got these Google Glass, which is something that was available for a while. Google has actually canceled that project. But there are actually some of these devices out right now for cyclists that create what is called a PAN, or a personal area network. And the device connects to your cycling computer and displays your speed and power output projected directly onto the glass, so you don't have to look down onto a cycling computer to see your speed. We have smartwatches. So we have watches that allow us to get our emails, allow us to get alerts, all types of items. We have the ability to control our homes remotely. We have the ability to sense whether or not we're out of milk. That's an example that's been shown before. We have internet-connected TVs. In fact, they're so cheap now it's ridiculous. We just had big sales in the United States dealing with holidays, and it's amazing how cheap televisions, smart televisions have become. And then we've got set-top boxes. So our normal computer gaming consoles, what used to be like TiVo, now DirecTV, those types of things that are integrated. What can we do with them? Everything. It's really amazing. Recently I bought a vehicle that has Android Auto in it. Allows me to put my phone into the car. I can receive emails. I can just tell Google to navigate to a certain place, and it uses Google Maps to navigate using my car's display. So pretty amazing the world we live in today and the connections we live in. It's really expanded our world too, because now, like I said earlier, I can text people in Germany. I can text people in the UK. I can Skype with someone in Canada. So you get a bigger world view than you had before, when we were very limited in the communities we can interact with. What do we send? Well, we send data. And data is of a couple different types. One is volunteer data. In other words, something I put in. I either like it, I give you information, I put a video up. This video right here that I'm giving you, this is data. You've now got my voice in a video. Inferred data, you can look at purchasing patterns. You can look at your current debt to get your credit score. You can look at your payment history. So that is an example of inferred data. And then last we got observed data. And this is where like you turn your location on your phone, and your phone pops up and says, hey, you're at XYZ Corporation. Will you leave a review so that it will help other people? Now, that scares me in a lot of ways, because it suddenly says that my phone knows exactly where I'm at. But at the same time, it's useful because my phone can pop up and say, hey, you're in a new city. I know you like Thai food. Here's a really good Thai food place that's 1 block away from you. So the connected world has its challenges, but there are a large amount of items that are available to us now that simply were not available before we had these connected networks in the world. So what do computers actually send? Well, computers, I tell people, are one of the dumbest inventions ever. They understand a 1 and a 0. They are binary machines. So right now they send everything in bits. So a bit is a base 2 number. Well, a bit is actually a single item that is either a 1 or a 0. But binary code is a base 2 numbering system that is usually grouped by what we call a byte, which is 8 bits. And believe it or not, 4 bits are actually called a nibble. All right. But in order to send this information, we had to develop a system which could translate normal characters, alphanumeric characters, into a bit value. So the lowercase a translates into 0110 0001. Now notice an uppercase A translates into a completely different set of ASCII bits. So these codes can represent any type of information. We can use it to represent characters. Okay, here's a V, well, a B. You notice it changes the bit translation here. And basically we take all of our data, our information we want to send, convert it into bits, send it out through the internet. And what we actually do is we encapsulate the information using certain standards. It's sent across a certain media or medium, and then it's de-encapsulated on the receiving end. So how do we get them moving? Well, remember, the computer takes the data, whatever it happens to be, this video for instance, converts it into bits. And then those bits are streamed or sent across some physical media or medium. Now, if it's sent across copper wire, it's turned into pulses of electricity. If it's sent across a fiber optic cable, it becomes pulses of light. And depending on the time interval and the, especially for pulses of electricity, time interval and the amplitude, you can look and see whether it's a 1 or a 0. With a pulse of light, if there's light during the time interval, it's a 1. If there's none, it's a 0. Then you also have radio waves, where it can be converted into 1s and 0s. So these are our 3 main ways of taking our bits and converting them into some form that can be transmitted from one host to another host. Now, each one of these transmissions requires a different media or medium. Electricity would be copper cabling. Pulse of light again would be fiber optic. And then wireless, this radio signal would be any type of wireless communication. So any of our 802.11 standards. And that's becoming increasingly more popular and common. In fact, I read recently that Google is thinking about abandoning Google Fiber in the hopes of actually creating more of a high-speed Wi-Fi standard that would be used. So how do we measure bandwidth? Well, we measure bandwidth based upon the number of bits per second. Now, the bandwidth is, there's a couple things you need to think about with bandwidth. Bandwidth is the capacity of a medium to carry data. By that I mean, imagine bandwidth to be a garden hose, all right, or a fire hose. Let's say a fire hose. If you have a 4-inch fire hose, it can carry, at its maximum bandwidth, 4 inches of water in that hose, all right, over a period of time. So if you were looking at 3 seconds, you look at, is it carrying the full 4 inches of water? That's bandwidth. That's the maximum that the medium can carry. Throughput is the amount going through the medium at any one time. So on that fire hose, bandwidth is the max. So if you turn it on full blast, 4 inches of water through that hose will be all you could get. If, however, you turn it on half and you're only putting 2 inches of water through the fire hose, your throughput is 2 inches worth of water. Your bandwidth is 4 inches. There's another item in there called goodput, which is in data, it's how much, or in data networks, it's how much actual data is being carried over the medium instead of control data. Okay, so there's always some overhead and control data. Here's some of our common items. So if you hear bits per second or you hear kilobits per second, that's 1,000 bits per second. Megabits per second, okay, so that's 1 million bits per second. And then gigabit and trillion terabit per second. So these are our common bandwidths. Now, how do we measure throughput? Here again, this is our a very common look for measuring throughput. Now, again, bandwidth and throughput are different. The cable coming in your house can do more than likely much faster bandwidths than the throughput that's coming to your house. So the way of measuring throughput is to look at the amount of data being sent and received, the types of data being transmitted, and the latency created by the number of network devices. So again, it goes down to our bandwidth may be 4 inches worth of water, but we may only be able to put 2 inches of water through it because that's all we can get from the fire hydrant that we're connected to. So that is an important concept. Also, another thing you need to think about is a concept called latency, and that's the amount of time that is added in delay as information goes through networking devices. As you move through your career, and as we look a little more in this particular course, you'll learn about a thing called the OSI model. You'll learn about how data gets, again, encapsulated and then de-encapsulated. And on certain networking devices like routers, a higher layer of information needs to be looked at before the data can be moved forward. That introduces delay into the movement across the network. For now, it's enough to know that latency is the delay added to data traveling over a network due to devices it goes through. Here's a little drag and drop activity that's available in the chapter. Now, clients and servers. Very simply, clients receive services from a server. All right. Servers provide services. Now, we have two different types of networks out there in the world. We have server-based networks and we have peer-to-peer networks. In a server-based network, you have clearly defined clients and clearly defined servers. In a peer-to-peer network, okay, you actually have clients that are providing both client services and also giving out file services. So peer-to-peer in most networks today, unless it's a very small network, we try not to use peer-to-peer. Here we see email servers, web servers, file servers, and then web clients, email clients, all those available. All right. And again, here you can have multiple roles. Here's a server that has both email, web, and file servers installed. So let's say you have a small office, home office. You have one server, it's providing all those services to your clients. So a network that has this, in other words, one file server, one web server, one email server, those are not as common as you would think, especially in smaller organizations. You'd have one that had a file server and an email server on it. The web server would probably be separate for security reasons. You'd put it out in what's called a demilitarized zone, or DMZ. Another drag and drop activity available in the curriculum for you to complete. So what are network infrastructure? Now, I talked to you a little bit about the intermediate devices. We have end devices, and that's devices that provide or receive services, such as a server or a client. Then we have intermediate devices. So these are the devices that data goes through. For instance, your wireless router at home that connects you to the internet. That's an intermediate device. All your PCs in your house connect to this wireless router, and then that is connected to the internet via your ISP. So these intermediary devices, firewalls, call managers, switches, for us what we're going to really focus on in this class are routers, wireless routers, and switches, and maybe wireless access points. These are all devices that you connect host to. Now, so intermediate devices. End devices are those hosts that provide or receive services. So your printers, your tablets, your phones, gaming consoles. And then last but not least, you have the network media and what hooks all these together. It can be LAN media, which could be copper, so unshielded twisted pair cabling. WAN media, which could be typically fiber of some sort. And then wireless media, and you have what's called a cloud, which is that nebulous thing you just connect your cable into and hope someone else takes care of it on the other end, as far as connectivity goes. So again, here's end devices. So we got to send something from this PC. We go to the intermediary device, the switch. It goes out to a router. The router makes a decision about how to route it across an internetwork or a group of routers connected together. It then sends it across that media. It will go to the other side to a router, be delivered to a switch, and then eventually get to the end device that it was supposed to go to. Now, end devices again can be printers, computers, tablets, telephones, teleconferencing devices, you name it, security cameras, even signage in stadiums now. We now have IP signage in many of the more modern football and baseball stadiums to where they can change the prices of items or say that this item is sold out or do a special on an item just by making a change on one computer that will then propagate out to all the signs. Here's an example of a peer-to-peer network that I mentioned before. In other words, here we have two PCs. They both are clients. In other words, this server or this PC right here is receiving files off of this PC. This would be kind of like your Plex server at home. Let's say you're serving out Plex to your Xbox or your PS4 or whatever. Your Plex server would be the file server. It's got your items, your movies on it you want to serve out. And then you've got a client that's going to go out and get those off of the file server. The print sharing would be a printer connected to a computer that you've got to connect to get information. These two PCs must be on in order for the file services to be available. Now, the good thing about peer-to-peer is cheap. It's easy to set up. It's less complex. It has a lower administrative cost because you don't have to hire an administrator to be dedicated to running the servers. The negative is there's no central administration, so there's no central security, which makes it less secure. It's not scalable. The rule is peer-to-peer networks should never have more than 10 devices in them, period. And because the devices have to act as both a client and a server, performance can be degraded. Now, the other would be a client-server network where you would have an individual server as we showed before, and that server would provide services to the client. A server-based network is more secure, it's more expensive, but it's more secure, more robust, more scalable, and a server-based network are what we're going to find in all of our modern business networks. So, how do we verify that a device is alive and running? Well, we can do that with what's called the ping command, packet internet groper. We can send a ping from one IP address, and basically just consider this, if you don't know what an IP address is, an IP address is just the phone number of a PC. And we can go across, and this basically picks up the receiver and says, hey, are you over there? And then an echo reply comes back. So an echo request is sent, an echo reply comes back. Now, because pings can also be used to do some pretty dastardly hacking and information grabbing, many networks do not allow ping to go across them, but on local networks, ping should work. So here's an example of how it works. Just type ping in the address, and then hopefully if it's not being blocked, you'll get a reply. Another command is called Traceroute, and Traceroute actually uses ping, and it uses a feature of ping called the time to live. Typically, a ping has a time to live of, depending on the operating system, up to 30 or 32, or maybe even more, depending on whether or not you set it yourself when you do the ping. But the ping with Traceroute goes out with a time to live of 1 to begin. So that means it will go to the first router, and the time to live field is decremented by 1, which has it timeout. And then London would return the information and say, hey, okay, you got here. Traceroute then sends a ping with a time to live of 2. So it would jump through 2, and then you know you're at Paris. And then finally, it sends out a ping with a time to live of 3, which will get all the way to the destination and come back. This shows you the path a piece of data, a packet, is taken across the inner network. Now, that is very simply how networks work. Networks are a collection of devices, and they can be small networks, small office, home office. They can be local area networks, a network within a limited geographical area. They can be a network that is a wide area network, a group of networks connected together. All of them share some common features, and that is they are comprised of end devices like PCs, phones, tablets, intermediary devices like routers, switches, access points, wireless routers, and also media, and that is either copper, fiber, or some type of wireless medium that these signals go across. All of these are connected together to build a network. We have a lab in this chapter. There's a simple lab of building 2 PCs and a switch, and then putting an IP address on them. I'm going to very quickly do a example of this using a program in the Cisco Network Academy called Packet Tracer. And I'm going to pull out, and it takes it a second to load here. Okay, so Packet Tracer is opened and we have it up. This is a simulation engine that's used in the Cisco Networking Academy. What I'm going to do is I'm going to build a network that simulates the network that's shown here. One of the things that would be best, obviously, is that you get 2 PCs, some straight through cables, and a switch, and do this lab. But with Packet Tracer, I can actually go down here. I can grab a switch, and I can pull out a 2960 switch. I can go to end devices, find my PCs, and I can pull out a generic PC1, or PC0, it always does. I can then grab my cables, and I can go get a straight through cable, click on the PC, connect the fast Ethernet to FA06, I think it was. It really doesn't matter for the lab, but 06 and 01. Then I'll do 01 with this one. So I do 01. You see the cables actually go into spanning tree on the switch side. And then I can go into each PC. I'm going to slide this up a little bit so I can see the IP addresses. And so I'll use this as PCA. And this is the only thing that's a little bit different. It doesn't actually show you, it's not a normal IP setup for Windows 7 or Windows 10 or any of those things. It's just a kind of a little interface here. 192.168.1.10 tab, and there's your mask. I'm not going to set a default gateway because there's no router in this situation, so you don't need it. Go to the wrong one. I meant to go to command prompt. Go to command prompt, type in IP config. Make sure my IP address is in there, 1.10. It is. I'm going to move over PC0 and PC1. I'll bring it up. Go to desktop, IP address 192.168.1.11. Again, no default gateway, no DNS needed for this particular item. IP config, and you see it's 1.11. Now I can ping 192.168.1.10, and hello 1.10, are you there? And 1.10 replied, yes I am. And in fact, can't remember if this actually works, but yeah, it does. You can see here if I do an Arp-A, which is a command to show what's called the Arp Cache, you can see I've got the MAC address, which is the physical address of PC 1, in this case PC-B actually, in my table, so I've received the ping here. And I can actually go over here 192.168.1.11, and so we've got bidirectional communication from 110, so 110 replied, and then when I ping 111, 111 replied. And that's the gist of this particular lab. Now this slide walks you through doing it on a Windows 10 box or Windows, I believe it is Windows 10, Windows 8, same difference. But we just did it inside of Packet Tracer to make it a little bit easier for us to see. And we can also see here that this is, you get a little more information when you're doing ipconfig on a true device, and you can do ipconfig all. I'm using the up arrow here to do this, /all, and it does show me a good amount of information, but it's not the full amount of information that you would see on an actual PC. So this simulation engine that is Packet Tracer is very neat. It has some cool features too that we can actually just do. If you want to do a quick ping, you can just click from here to here, and it actually will go across and then show you whether or not the ping was successful. So it's a neat little device or a neat little simulation engine that can be used to watch packets go by. And you can go look at a packet, look at how the information's in there, the outbound PDU protocol data unit. So, I hope you enjoyed this particular lecture on Networking Essentials Chapter 1, and look forward to seeing you in future chapter lectures.